Welcome to topic 7.3. We're continuing to look at Lewis structures, but we are going to look at them on instances where we don't have enough electrons. So we're going to be looking at multiple bonds today. So you can see I'm back in my studio making my award-winning video. So hopefully this one is a better experience than the last one. Video making from my home just never goes well. So on to the real deal here. So there are instances where you do not have enough electrons to complete the octet. So everything that we did on our first lesson, 7.2, you had enough electrons to complete the octet of your central or central atoms, and then you were also able to complete the octets of any outlying elements that were not hydrogen, because if you remember, hydrogen doesn't need an octet, but you were able to make everybody happy and get them enough valence electrons. So when you run into the scenario of not all electrons are present, not enough electrons are present, needing to get everybody to their octet, we then can have a double or triple bond. And so that's what I'm going to show you today and how you find that. So there are certain elements that are able to do this. And so I've just come across a couple of tips and tricks from this other teaching individual that I have never seen for doing Lewis structures. So you guys are kind of guinea pigs a little bit. And so the first thing I came up with is, I know that it was carbon, oxygen, nitrogen, and sulfur, but I've never thought of making an acronym with it. So CONS is your way to remember that these are the four elements that can make multiple bonds. Other elements on the periodic table don't have this capability. The next thing, and these tips really aren't going to make sense quite yet, but they will once we start practicing with it. So the big thing students struggle with, and maybe we can talk about this more at the end, is the idea of how do I know when I need a double or triple bond versus when do you have all single bonds like we did again back in 7.2. So maybe I'll kind of keep this off to the side and we can refer to it. You definitely, again, still need your periodic table. And so to start out, a lot of what we've done is the same. We're just going to see a slight spin on what we have going on here. So the first thing we need, just like anything else, is a formula and valence electrons. Well, oxygen, it's an element, but it is a molecule in that it's bonded to itself. So all the oxygen in the atmosphere is O2, and that has to deal with the reactivity of oxygen. And so it's diatomic, and there's some other elements that do that as well. And we'll talk about those more later on. So anyways, oxygen is in family 16. Therefore, oxygen has 6 valence electrons. And then the next thing is we do see a subscript of 2 here. So when we look at this, we have oxygen. There's 2 of them, 6 electrons. So in total, there is 12 valence electrons. Okay. So the first thing we would then do in drawing the Lewis structure is get our central atom. Now, in this particular example, we don't really have a true central atom because there's just 2 things present. So what we have is O bonded to O. So if you remember, that single line is a single bond, and that represents 2 electrons. So the goal now is to get each of these to have a complete octet. And so we do that by placing lone pair electrons around them. And so when we do that, I now have 2 electrons in my picture. So here is 4, 6, 8, 10, and 12. Remember, I told you you have a kind of like a allowance here, or a spending limit. And so we can only spend 12 electrons. And so I have all my electrons accounted for in this diagram. However, when I cover up this one on the right-hand side, this oxygen on the left is great. The oxygen on the right, however, is not. And so when you do not have enough electrons to complete the octet, and you're working with one of those CONS elements, not copper, carbon, oxygen, nitrogen, and sulfur, that means they can have more than one pair of electrons that they share. So what you do is you take the electrons from the element that has the complete octet. So again, it's always from the complete octet. And we're going to move that in here and make a multi-bond. So what that looks like, what that results in, is we look like an equal sign between the 2 of them. And what I've done is on the oxygen on the left, I have 2 sets of lone pairs. And now the oxygen on the right still has its 2 set of lone pairs. So the equal sign is a double bond, and that represents 2, 4 electrons. So when I cover up the oxygen on the right, I have 2 bonds here. So that's 4 electrons, 6 and 8. This has a complete octet. Over here, I have 2, 4, 6, and 8. That has a complete octet. And so from there, I have spent all my electrons, everybody's happy, and I'm done. So how I know I need a double bond is when you run out of electrons to complete the octets. You cannot just add electrons that are not there. So the next example, this is a organic compound called ethylene, so C2H4. So we need to start out with valence electrons. So we have carbon and we have hydrogen. Looking at the chemical formula, we have 2 carbons, we have 4 hydrogens. Then you would access your periodic table. Looking at our setup, carbon has 4 valence electrons, hydrogen has 1. So we have 8 plus 4, so we have a total of 12 electrons to spend. So this example is similar to a couple in your handout from your homework and a couple from the notes. We don't have a true central atom, so what we do here is we start by placing the carbons as the center, and we split the hydrogens up amongst them. So there's 4 hydrogens, so each of them can take 2. Don't forget, hydrogen is content with just the bond. So we're not looking at completing the octet. We bond it, it gets its 2 electrons, and we're done. So what I have to look at is these central carbons. So this carbon here on the left has 2, 4, 6 electrons. It's symmetrical, so we have the same thing going on with the one on the right. So they each have 6. That means they need 1 more. So I'm going to go ahead and add a lone pair. And if I look at where I'm at, I have spent 2, 4, 6, 8, 10, 12 electrons. I have spent all of my valence electrons. So again, this is my little red flag. I was able to make my carbon on the left happy and give it its 8 valence electrons, but however, I was not able to do that for the one on the right. So again, what you do here is you take the lone pair of electrons from the element that is complete, and you move that between the element that is complete and the one that you're trying to finish. So when I draw this diagram for once I'm finished, it's going to look like this, with a double bond between the carbons, and those 4 hydrogens remain. So again, when I cover up this one on the right-hand side, I have 2, 4, 6, 8 electrons because I have 4 bonds. Again, it's symmetrical, so it's the same thing. The double bond gives this one on the right 4, and then the 2 between the hydrogen gives you another 4 electrons. And so again, last thing is 2, 4, 6, 8, 10, 12. I have all 12 electrons, and everybody has a complete octet. Therefore, you are done. If you want to take a moment, actually don't do that quite yet. I was going to tell you to pause and work this one out on your own, but let's not do that quite yet. So nitrogen is like oxygen. It's another diatomic. So the nitrogen in the atmosphere is N2. So we have 2 nitrogens. Looking at your periodic table, it has 5 valence electrons. Therefore, it has 10 electrons present. So like oxygen, there's no true central atom. Bond our nitrogen together. And so I have spent 2 electrons. So that means I have 8 left. So here is 4, 6, 8, 10. So my nitrogen on the left-hand side is complete. You can see the nitrogen on the right is very incomplete. It needs 2 more sets of electrons or 4 more electrons to get to that point. So like before, we need to share more than just 1 set of electrons. So what we need to do now is the one that is complete. Again, you always take from the one that is complete. That is the one that can then start to share extra pairs of electrons. So if I take this set and move them in, that would then give this one 2, 4, 6 electrons. It needs 8. So we can take and move a second set in, and that would give me 2, 4, 6, 8. So let's draw that out and show you what that really looks like. So the resulting Lewis structure has the nitrogen triple bonded to a second nitrogen. Each of them will still have a lone pair that it then keeps to itself, and those the lone pair I just put down here at the bottom. So again, a couple of things. Do I have 10 electrons? So 2, 4, 6, 8, 10. So that is good. I'm looking at, is everybody's octet complete? So this one on the left, I have one lone pair and this triple bond. So again, 3 lines is a triple bond. Therefore, it is 6 electrons. So I have 6 electrons plus the 2. That gets me 8. It's symmetrical with the right-hand side. So everybody has a complete octet and all electrons are spent, and we are done. So the last example is hydrocyanic acid. And I never gave you guys this one on any examples because this one actually really doesn't follow the naming rules. So we see hydro, so we think, okay, hydro means binary. And then we have cyanic. Well, that part isn't an element. So it actually comes from the polyatomic cyanide. So H is a +1. Cyanide is a -1. So our formula here that we're working with is HCN. So when we go to make this Lewis structure, we have 3 elements, hydrogen, carbon, and nitrogen. Hydrogen, we have 1, 1, and 1. So when we go to the periodic table, hydrogen has 1 valence electron. Carbon is in group 14, therefore it has 4. Nitrogen is in group 15, therefore it has 5. So I add basically those up to get 10 electrons to spend. Now the trick with this one is we have 1 of each. So you have to decide what is your central atom. So when it comes to deciding that, hydrogen can never be in the middle because you would have other things bonded off of it, and that would go past its 2 valence electrons. So the last thing is between carbon and nitrogen. Carbon is always your central atom if it's an option. So we're going to put carbon in the center, nitrogen and hydrogen off to the sides. You could have these flip-flopped. You could have it going this way for now. So again, as long as you have carbon in the middle and a hydrogen bonded off of that carbon and a nitrogen bonded off of that carbon, we're good. So we've spent 2 electrons, or 4 electrons in 2 pairs. I'm going to go ahead and complete the central atom. That's usually where I start, is I like to complete the octet on the middle. I know I don't even need to look in hydrogen's direction because hydrogen is not going to need any more electrons. And then from there, I have 2, 4, 6, 8. So that means I have 2 electrons left to spend. So once I've got to that point, I need to start looking for octets. We just said hydrogen's good. I'm going to ignore it. Looking at my central atom, it is good with its 8 electrons, 2 lone pairs, 2 bonded pairs. Nitrogen, however, has a bond and a lone pair. Therefore, it has 4 electrons. It needs 4 more. This is the part that students forget. Is you always take electrons from the central atom. Let me just take a second. Don't draw this on your paper, but let me explain why. If you take these lone pair from the one that's incomplete, this is what's going to result. So there's a few issues with that. The first issue is nitrogen now still only has 4 electrons. So that didn't resolve a single piece of the puzzle. The other thing is carbon now has 2, 4, 6, 8, 10 electrons. You've gone past its octet, and that is not the correct answer. So what really needs to happen, and let me just resketch this, is when we do this, we have carbon in the middle, hydrogen, nitrogen, we had this, and this. Okay, so you always take from the one that is complete, and you share with the one that's incomplete. So what happens is this is going to share towards the middle. But again, we said nitrogen needed 4 more electrons to get to complete. So in this case, this one is also going to require a triple bond. And so when I draw this out, what results is we have hydrogen with its single bond, because you will never have multiple bonds with hydrogen. Carbon graciously shared its lone pairs with 1 nitrogen, which still had the lone pair. Again, you always need to make sure you didn't overspend. So we have 2, 4, 6, 8, 10. That is good. The next thing I want to look for is complete octets. Hydrogen is good as soon as you've bonded it. Carbon in the middle has 4 bonds, 1 single and then a triple, so it has 8 electrons. Nitrogen has that triple bond, so 6 electrons are stored there. And then it has a lone pair, giving it 8. So this is the correct Lewis structure. This is not. So again, what you're looking for here is, do you have enough electrons? When you do not have enough electrons, this is where you form a single, go from a single to a double or triple bond. If you have any more questions, need any more help, if you're feeling a little lost and want extra practice or just some one-on-one time, please reach out to me and I will gladly have a Google Meet and we can work through some of these. Otherwise, good luck on your homework.